This question belongs to compiler design subject and was asked in GATE CSE 1991. So the question states, the arithmetic expression a plus b into c minus d divided by e whole power n is to be evaluated on a two-address machine where each operand is either a register or a memory location with a minimum number of memory access of operands. The number of registers required to evaluate this expression is the number of memory access of operands is. So we have been given an expression and we have been provided with the information that we are having two address machine. Two address machine means we will be having two addresses. Either it can be register address or memory address, in which each operand is either a register or a memory location. We need to find the number of registers required to evaluate this expression and the number of memory access of operands in the case where it should be minimum. We should be having the minimum memory accesses. So for this there is some preliminaries assumptions. Let me tell you those. So we will assume that every ALU instruction is of the form like it will have opcode, it will have operand 1 and operand 2. So what we will assume? We will assume that every ALU instruction, which is a data manipulation instruction, is such that the first address of the instruction is the destination. It will serve two purposes. It will serve the destination purpose as well as the opcode 1 purpose. It will serve as the destination as well as the address of the first operand, and it is the address of the second operand. Sorry, it's operand, not opcode. Operand 1 and operand 2. There is some confusion. These are operands and this is opcode. So we have operand 1. Suppose we have something like add R1 followed by R2. So this means that we will get the value from register R1 and then we will get the value from register R2. We will add them, and register R1 is the destination which will store the sum R1 plus R2. And here this double star is equals to exponentiation. Exponentiation means power. So here, as this is a two address machine, we have been given that this is a two address machine where each opcode is either a register or a memory location. So what are our priorities? First priority is we are given a minimum number of memory access. So we will have minimum memory access. And what is our second priority? Second priority is this. The number of registers, we need to find the number of registers and it should be minimum registers. So these are our priorities. Now let us see how we will do this. So I will tell you each operation that we need to do to evaluate this expression. So let me first write this expression so it becomes more clearer to a plus b whole star c minus d divided by e star star l. So I will write the operations and tell you the number of registers and the memory access. I will tell you over here. So first what will happen is that we will first of all bring the value a, this a, into register R1. So we have a one memory access. So one memory access is done. Okay. Now what we will do? Then we will do add R1 comma b. So what it will do? It will sum the value of R1 and with the value b. So R1 is a. So we will do a plus b and it would be stored in register R1. So we have used the register R1 and we have second memory access here for this b. So we have the second memory access for b. Let me write. We have memory accesses for what things? We have memory access for a, then we had a memory access for b. Then what we will do? We will then do multiply R1 with c. So what R1 has? R1 has a plus b. So we will multiply it with c and store it in R1. So this is the current value of R1. And what are the memory access? We have a memory access for c and we haven't used any extra register. It's R1 only. Now R1 has a plus b into c. Now what we will do? We will bring into the register R2 the value e. So we have a memory access for e and we have used another register R2. Now what we will do? We will do exponent R2 with L. So we have a memory access for L. We haven't used any extra register. And what we have done over here, we have done R2 will here R2 will store R2, the value of R2, which is e power L. So which is equals to e double star L. So this is the contents of R2. Now what we will do, we will bring into the register R3 the value of D. So we will have a memory access for D and we have a register R3. Now what we will do, as here D is the first operand, we will bring it into the register because first address in the instruction is destination as well as the address first operand. Thus we will bring R3 first. Then what we will do, we will do divide R3 by R2. So what we will do, R3 equals to R3 divided by R2. So we will have R3 equals to, what is the value of R3? R3 has D divided by R2. What is value of R2? E whole power L. So do we have a memory access? No. Do we have an extra register? No. These are capital R's. Now what we will do? We will do subtract. So we have both these things. Now what we will do? We will do subtract R1 and R3 and store it in R1. So R1 has this, R3 has this. We will do hold this and store it in R1. Do we have an memory access? No. Do we have an extra register? No. And we got our answer. So we have used 3 registers and 1, 2, 3, 4, 5, 6 memory access. So the answer is, we will be using the number of registers is 3 and number of memory accesses are 6.